Hello and welcome to the fourth video or fourth set of videos on kinetics. So here's how we want to start today. I want you to think about this reaction, A plus B goes to C plus D, and I want you to draw a graph of what you think. Let's do concentration of reactants. You can just kind of think of it as the sum of the concentration of the reactants and overlay that with concentration of products versus time. Okay? Just use the same graph. Tell me what you think they're going to look like. So pause it, draw it, and then compare to what I have. So a lot of chemistry students, when they're first starting out, would say that the graphs would look like something like this, where, as the reaction progresses, you're using up the reactants. So they should just have a linear decrease until there's none of them. And the products, on the other hand, should start at zero concentration, because there aren't any initially, and should increase, okay, with roughly the same slope, right? And a lot of people will say this, but the problem with this is that a lot of reactions don't behave like this. Reactions that go to completion, meaning all of A plus B get turned into C plus D, would look like this. But most reactions don't do that, okay? Rather, this reverse reaction, C plus D goes to B plus A, so the reaction going this way, is possible. And the fact that this reverse reaction is possible affects what this graph is going to look like. Okay? So what actually happens is that, let me label my reactants and products again. Concentrations of reactants and concentration of products. Okay, so my concentration of products are going to start at zero, but instead of being linear, what's going to happen is they're going to increase like this. Okay, and my reactants are going to decrease until they get to a time when they're not changing anymore. Okay, so the fact that equations or reactions can happen reversibly leads to something called equilibrium. Okay? And we're going to talk about this a lot. Okay? So to start, let's think about the same reaction. A plus B goes to C plus D. And I want to write, if I assume that this is a one-step mechanism, both directions. I'd like you to write the rate laws for both the forward and the reverse reaction based on this information. So go ahead and pause it and see if you can do it. So the rate for the forward reaction would be rate forward equals K times the concentration of A to any coefficient times the concentration of B to any coefficient, which in this case is 1. So these are both 1. And I'm gonna actually specify that this K, this rate constant, is actually K forward. The rate of the reverse reaction is just going to be rate reverse equals K reverse times the concentration of the products, which are going to be C and D. So concentration of C to the 1 times concentration of D to the 1. And you don't have to include these ones, but I'm going to include them today just to make everything a little bit more clear. Okay, so let's talk about what happens to the rates of the reactions as the reaction progresses. Okay, so initially, there are no concentration of products, which means that the initial rate of the reverse reaction has to be 0, because concentration of C and concentration of D are 0. All right, and the the rate of the forward reaction, on the other hand, is going to be quite fast because I have a high concentration of both A and B. Okay, but as the forward reaction continues, A plus B are going to get consumed, and C plus D are going to be produced. And as I do that, the forward reaction starts to slow down, and the reverse reaction starts to speed up. Okay, and eventually we're going to get to a point where the forward reaction has slowed down enough and the reverse reaction has sped up enough that the rate forward equals the rate reverse. Okay, and we call this state here equilibrium. All right, equilibrium is a dynamic state. Okay, that doesn't mean that the concentrations of A and the concentrations of B aren't changing. A and B and C and D aren't changing. It just means that that the rates of change for the forward reaction and the reverse reaction are both going to be the same. All right. So my sort of classical example of this is if you have, let's say that you have two islands. Okay. Here's one island. Okay, and here's a bigger island. Okay, and these two islands are connected by a two-lane bridge. Okay, here's my bridge, and I've got cars going this way. Here's my awesome car that might also be a spaceship in a later episode. Who knows? Here's my car going this way, and here's my car going this way. Okay, and let's say that there's bumper-to-bumper traffic on the bridge. Okay, and that the cars going this way are moving at the same speed as the cars going this way. It doesn't necessarily mean that the number of cars on this island are going to be the same as the number of cars on this island. What it means is that the number of cars on this island aren't going to change, right? Because for every car that leaves, another car enters. Okay, and same thing over here. So this is just like a kind of silly example of equilibrium. It's a dynamic state, meaning it's constantly changing, constantly moving. This car here might be here, it might be here, it might move back and forth across. Who knows? Okay, that's not really that important. Individual particles aren't really that important. The bigger picture is this overall dynamic state. Okay, so that's equilibrium. We're just getting to a point where the concentrations of reactants and products aren't changing. Okay, so what that'll mean, and the interesting thing here is if I make a graph of the rate of the forward reaction versus the rate of the reverse reaction. Okay, the reverse reaction, as we said, should start at 0 and increase. Okay, and then it's going to tail off. And the rate of the forward reaction is going to decrease until it also tails off. And it'll tail off at the same point. And when these have exactly the same value, okay, circle that in black. Okay, this is equilibrium. Okay, equilibrium. Yay. All right, so I want to consider a couple different examples graphically, and we'll come back and describe these mathematically in a little bit. All right. I'm going to start with my same concentration of reactants and concentration of products. And I'm actually going to be smart here. I'm going to copy that so I can use it again on the next one. Okay, so let's say that I get something that looks like this. Okay. Okay. This is still a state of equilibrium, right? But in this case, the concentration of products is going to be much higher than the concentration of reactants once they hit equilibrium. Okay. And I'll say, by the way, this two-sided arrow, or one that's like this, this is how we denote equilibrium or reversible reactions. Hopefully you remember that from some other chapter. Maybe it was chapter 1. Okay, I don't expect you to remember that. But here it is. That's how you represent reversible reactions. Okay, so in this case, concentration of C and D at equilibrium are going to be much larger than concentration of A and B, and so we sort of have special terminology to describe this. Okay, we say something along the lines of equilibrium lies to the right, or you might hear favors the right, or might favor the products as it's written, something along those lines, okay? So what about, and I was smart, so I can just go bam. What about a case that looks like this, where, let me get back to my drawing tool. Uh-oh. Wah, wah. Color change. All right, there we go. Where my reactants look like this and my products look like this, okay? And I get to a point where my concentration of reactants aren't changing, my concentration of products aren't changing, okay? Here again is another example of equilibrium happening, okay? But in this case, you're going to end up with a larger concentration of reactants. So this, we would say, favors the reactants, or equilibrium lies to the left, okay? You sort of, you got what I'm saying here, hopefully? So let's not talk about describing this mathematically, okay? And to do this, I'm going to add coefficients into our sample equation here, where x and y and n and m are just the coefficients in front of each of these chemical species, okay? We know that at equilibrium, so at equilibrium, okay, rate forward equals rate reverse, okay? Fair enough, right? That's what equilibrium means, that the forward rate and the reverse rate are the same. Now, I have rate laws for each of these. So the rate law for the forward was K forward times concentration of A, and now that I've added the coefficient in, that's A to the X times concentration of B to the Y. Now notice that I'm assuming one-step mechanism, okay? And that's going to be assumed for everything that we do in intro chemistry. In college, you'd add on to this and you'd learn what to do with multi-step. But for high school, for intro chemistry, we're just going to assume everything is one step, okay? So the rate of the reverse, we said, was Kr over concentration of A, or sorry, not A. Silly Mr. Ryan. Concentration of C to the M times concentration of D to the M. All right, now I'm going to get my constants, my rate constants, on one side, and I want the forward reaction on top, okay? Because the rate constants sort of give you an idea of how fast the rates go. So a large rate constant means a very fast rate, and a small rate constant means a very slow reaction. And if I want to know like how fast this reaction progresses as written, I want to compare the forward rate, the K forward, to the K reverse. So I'll divide both sides by KR, okay, to get rid of this bad boy. All right, so now I've got KF over KR, and I just have to divide both sides by A to the X, B to the Y. Sorry, concentration of A to the X, concentration of B to the Y. I shouldn't have A to the X, concentration of B to the Y. All right, so now I get KF over KR. Now, this seems kind of funny. I have a constant divided by another constant. And if you take a constant, let's say the number 3, and you divide it by another constant, let's say the number 2, you would always get a constant. Let's say the number 1.5. So if I have this constant divided by this constant, I know that that's always going to be a constant. All right, and here's where you're really going to start hating me. This constant we write as a new constant, and of course, because this is chemistry, it's a K. But this time it's not a lowercase k, it's a capital K. And in your textbook, they just leave it as that. So rate constants are lowercase k's, and equilibrium constants are capital K's. All right? I'm not a big fan of that. I think it's maybe just a little too confusing. So I actually label these KEQ, equilibrium. Okay? And this, my friends, is an equilibrium constant. And we're going to talk more about that in a bit. And our equilibrium constant just equals this mess over here. So concentration of C to the N over concentration of D to the M over concentration of A to the X times concentration of B to the Y. So you just have to remember it's products over reactants. All right, you have to remember that. Maybe like come up to your friends in the hall and just say, remember, it's products over reactants, and they'll look at you like you're a crazy person, but it'll help you remember. It'll help them remember too, and they'll thank you in the long run. All right, so this bit here, KEQ equals all this awesomeness. This equation is called the equilibrium expression. Okay? So I want to go back and I want to see how this applies to the last two graphs that we made. All right? So, and before I do that, I'm actually going to copy, oh, not you, come on, there we go. I'm going to copy all this stuff in here, and I'm just going to bring it with us when we go talk about these graphs. V, and then, well, that's not ideal. But we'll kind of leave it there because I can't figure out how to move that now. So if I look at this at equilibrium, so when we're out here, if equilibrium lies to the right, equilibrium favors the products, your concentration of products are going to be huge compared to your concentration of reactants, which means that for reactions like this, KEQ is going to be much, much larger than 1, right? If they're equal, if the concentration of reactants and concentration of products are equal, then KEQ is just going to be 1. So they're kind of like 3 different states here, right? There's KEQ is greater than 1, there's KEQ is equal to 1, and then there's our friend down here, right? This is going to be KEQ. Now, concentration of reactants is greater than concentration of products, which means that KEQ is going to be less than 1. All right? So that's just some interesting thing with the equilibrium constant. All right, now a couple more sort of tidbits about the equilibrium constant. Okay, tidbit number 1, and these are very important. Okay, pure solids and liquids are not included. Well, that seems odd, but if you think about it, it makes sense, okay? If you had, let's say, pure liquid water, okay? You know that liquids aren't very compressible, which means it has a definite volume, and the volume is not going to change. And so the concentration of that is not going to change. Or what's going to happen is if you use water in the reaction, the amount that the moles of water are going to decrease, which would also decrease the volume by the same amount. So your concentration of pure solids and pure liquids is never going to change anyway. So they're just not included in equilibrium expressions, okay? So that's important. That's like super, maybe the most importantest, okay? The second thing to keep in mind is that KEQ is temperature dependent. And we'll talk more about that at a different time. But one of the sort of consequences of this is that in a lot of problems, they're going to give you the temperature for the equilibrium system that they're talking about. And people get confused by this, okay? They're like, why are they giving me this temperature? How do I use this temperature in the problem? And most of the time, you don't use the temperature. It's just important to the people who made the problem to include the temperature so that it's correct, okay? And the third thing is that there are no units, okay? And this is, there are no units. This is kind of a blessing and a curse because when you're solving for equilibrium constants, you don't have to worry about units. But there will be times when, like, maybe I ask you to find a concentration using the equilibrium expression, and you're not going to have the units to help you stay safe, okay? You know, we use units all throughout chemistry as a way to help us kind of figure out what we're supposed to do and check what we're supposed to do, all right? And this time, not so much going to be able to do that, all right? So it's a blessing and it's a curse, and we'll sort of see that more a little bit later. Here's our first example problem. At 25 degrees Celsius, an equilibrium mixture of gases contains 6.4 times 10 to the minus 3 moles per liter PCl3, 2.5 times 10 to the minus 2 moles per liter Cl2, and 4.0 times 10 to the minus 3 moles per liter PCl5. What is the equilibrium constant for the following reaction? Okay, so the first thing that I want to just highlight here is these units. okay? So we need to make sure that we have concentrations, right? Which we kind of we're kind of thinking about that in terms of molarity, right? Well, for gases, it's not going to be the same as the solution, so it's moles per liter of the container, right? Because a gas expands to fill its container. So that's just one thing to kind of be careful of, just to make sure that the units of what you're given are a concentration, because sometimes you'll just be given moles and you'll be given a volume, and you gotta adjust for that. Okay, so here's the reaction. Notice the two-sided arrow, which means that this is a reversible reaction. It's balanced. Okay, so from this I'm gonna write my equilibrium expression. Right, so KEQ equals concentration of products over concentrations of reactants. Okay, so concentration of PCl5 is my only product, and that's really to the first power because the coefficient is 1, over concentration of PCl3, also to the first power because the coefficient is 1, times the concentration of Cl2 to the power of 1. Okay, now that I've got that set up, I'm just going to ignore the 1s from now on. Okay, and I'm trying to find the equilibrium constant, which is this. I've got this, I've got this, and I've got this. So this is really just a very simple plug and chug problem. So 4.0 times 10 to the minus 3. Okay, and at this point, I'm just going to ignore units because I know that KEQ doesn't have units. Okay, these are all in moles per liter, so they're all in the same units. So I'm just going to ignore them for now. Concentration of PCl3, 6.4 times 10 to the minus 3 times Cl2, which is 2.5 times 10 to the minus 2 mole, sorry, old habits die hard sometimes. Don't need the units. Okay, and this gives me, with two significant figures, 25. So KEQ for this, the equilibrium constant for this reaction, is 25 at this temperature. All right, well, what about for if I write the reaction like this? So this is kind of going beyond the problem, but it's a good thing to think about and kind of know about. So what happens if I write the reaction this way? Well, it's just the opposite, right? So KEQ in this case would be products, concentration of PCl3 times the concentration of Cl2 over the concentration of PCl5. Okay, so I can plug numbers in, 6.4 times 10 to the minus 3 times 2.5 times 10 to the minus 2 over 4.0 times 10 to the minus 3. And that gives me 4.0 times 10 to the minus 2. Now notice that these are not the same, right? But if I look at this, okay, this down here, this equilibrium expression, is really just the inverse of this one. So if I took this one and I took the inverse, okay, and I kind of did something like this, where I took this and I put the whole thing over 1, okay, the PCl3 and the Cl2 would flip up to the top, and the PCl5 would be left on bottom, which is exactly what this is. All right, so what happens now, or I guess notice, if I label this for the reverse direction and I label this for the forward direction, okay, I can say that KEQ forward equals 1 over KEQ reverse. And just to prove it, let's take 1 over 4.0 times 10 to the minus 2. And what do I get? Oh, that's right, 25. Okay, so that just this is something that you can keep in mind. Sometimes this will be helpful, and it just goes to kind of reinforce some of the concepts.